Hello everyone, and welcome back to another Geostats lecture video. And in this lecture video, I want to walk through the local Morans I, which is a local measure of spatial autocorrelation. So as we've talked about in some of the previous videos, we're going from does the dataset experience spatial autocorrelation to the local Morans I, which is sort of trying to show you where that spatial autocorrelation is most prevalent. So a lot of this is going to look very similar to what we've done in the past. In fact, we're still going to be sticking with the same SPDEP package and the same Georgia dataset. So again, if you don't have this code copied by now, pause it, copy down these 4 lines of code. This is our package management right here. So I'm just going to run this code chunk to make sure that we have all the packages we need. Shouldn't be anything too crazy. Okay. So we now have all of our packages required. So the first thing that we're going to do is we're going to load our data. And our data is going to, again, be the Georgia dataset from the GIS tools package. Okay, so we now have our data in place. So in order to run the local Morans I, we need the same pieces of information that we did for the global Morans I. So that is, we're going to need our neighborhood connectivities, our spatial weights matrix, and then the local test. Okay. So let's go ahead and first start off with our neighborhood connectivity. So again, just in case we're unclear here, right, our NB, our neighborhood matrix, is going to be done from the SPDEP package using a function called poly to NB. Okay, right, and poly to NB takes in 2 parameters. The first is going to be the polygons of interest, which in this case is going to be Georgia. Okay, and then it takes in this parameter of queen. And for the sake of this example, I'm going to set queen equal to false. So we're going to be running this on the rooks case, which again just means that the polygons have to share a boundary, not just a vertex. Okay, so this is our neighborhood matrix done and dusted. If we go into our spatial weights matrix, so this converts that neighborhood connectivity into an actual spatial weights matrix that we would feed into all of the tests that we're going to run. So our spatial weights matrix is going to be, again, from the SPDEP package, right? And this is going to look exactly like it did in the previous module. And we're just going to call in from the SPDEP package the NB to list W. Okay. And again, this basically just has one parameter, and that's the neighbors, which is going to be our neighborhood connectivity, which we called NB. Okay, so if we run that, that's our spatial weights matrix done. So let's talk about the local test, because so far everything we've done now is just review. Let's talk about this local test for Morans I. Let's make sure our console pops up here a little bit. Let me scroll down just a touch. So the function that we're going to be using here is, again, from the SPDEP package. Specifically, it is the local Moran. Okay, so we're going to use the local Moran function. So if we do that, right, again, the local spatial statistic of Morans I is calculated for each zone, right? So we're calculating it for each individual polygon, okay? So if we look at the usage, right, the function, again, local Moran, takes in essentially 3 parameters that we care about. This X, this list W, and then this p_adjust dot method. And we're going to talk about all 3 of these in just a second. So X, right, this is just like the global Moran, where X is the variable that we're trying to test for autocorrelation. So in our case, it's going to be that % renter occupied again, just like it was in the previous module. List W, this is again our spatial weights matrix. So that's the SWM SWM variable that we just created over here, and this p-adjust method. So if you remember in the conceptual videos where we talked about the p-values associated with these local statistics, we talked about that idea of having that multiple comparison problem, where when you have so many different p-values being calculated, right, you have potentially hundreds. I mean, in this case, I think it's only 56 or whatever counties we have. Oh, sorry, it's 159. I misspoke. We have 159 polygons. So if you think about it, right, we have 159 different p-values being calculated. And if you think about what a p-value means, right, it's the probability of getting this value or something more extreme, right? So if you imagine just a default p-value of 0.95 or 0.05, right, that means that 5% of our data could be considered, we reject the null hypothesis 5% of the time just by chance alone. So if you think about the fact that we have 159 tests, right, that means at a minimum, 7.5 of these polygons could have a false positive, right? We could be rejecting the null hypothesis incorrectly. So what this p-adjust method does is it says, hey, how do you want me to take care of that? So this is just addressing that idea of the issue of multiple hypothesis issues, right? And so what we want to do for that, if we scroll down here, you have the p-adjust SP, which we're going to look in more to in another video. But for now, we're going to not keep the default as none, and we're actually going to use the method called Bonferroni. So what we do to run the test, let's actually go ahead and code this up. So let's call this local mi for local Morans I. And we're going to set this equal to, again, we're going to use the spdep package, local Moran. Okay. And you can see here we have X, we have list W, and we wanted to set the p.adjust method. Okay. So again, X is our data set of interest. So in this case, we're going to be calling our Georgia, G-E-O-R, if I could spell right, Georgia at data $. So now we're in the actual data frame. And we're going to go ahead and use %rural. I'm sorry, I misspoke earlier when I said that we were doing the % renter occupied. We're actually doing %rural. That was my mistake. So we're doing %rural, okay? Our list W, again, this is that spatial weights matrix that we calculated in the previous line of code right here. So hopefully you understood what that was doing. And then p.adjust.method. So again, this is going to be taking in a string, and we're going to call it Bonferroni. And hopefully I didn't butcher that. Actually, let's go ahead and just click p-adjust. So this is the p-adjust method here. So this is what's being called under the hood. So this is what's actually adjusting our p-values to account for the multiple comparison problem. So we want Bonferroni, just to double check my spelling, B-O-N-F-E-R-R. See, I did spell it wrong. There we go, Bonferroni. So if we run this, okay, we don't get any errors. That's always a good sign. Let's examine the output. Okay, so let's start off by just calling the variable itself just to see what's in there. And you'll see here that we have we're using up a lot of console space here. But if we scroll up to the top, you'll see that we have li, eli, var l, that's ii, and z.ii. And then this pz, this right here. Okay. So this right here, this first column, this ii, this is our local Morans I calculated for each polygon. So this is the actual test statistic right here. Okay. Then over here, this PRZ greater than 0, this is our p-value. Okay. So this is the statistic, and this is the p-value. So let's go ahead and plot the results. So we're going to use tmap. So tm shape. Actually, before we do that, we actually have to join these results back to the data set. So actually join results to the data set. So we're going to do GEOR Georgia at data. I'm going to make a the Morans I. I'm going to set that equal to loc underscore mi $. And then I'm going to set it equal to II. Okay. I have done something wrong. Okay. So apparently the output from loc Moran I forgot, is not actually a data frame, so we have to convert it to a data frame. So if we do loc df equals data dot frame to convert the local Moran I. Now we should be able to join the results, but this needs to be loc df. Okay, so if we run that, we create a data frame, and then we do that, and oop, that needs to be $sign now. There we go. Got myself all confused. All right, so now that adds the I value, and then if we do the $sign, if we do the loc underscore mi underscore p-val, this is the p-value, and we want this to be loc underscore df $sign, and we want to use this pr.z.zzz.0. Okay, so this is what it changed the name of the p-value into. So if we run that, all right, so now just to confirm that everything works, I just want to double check the head of the GEORGI at data. Run that really quick. Okay, so we've got some columns here. So we have local mi and local mi $sign p-value. Okay, so let's go ahead and just quickly plot up some things. Tm map equals tm underscore shape. Shape equals, and then we're going to do GEORGIA for Georgia. And then I want to add the tm underscore polygons, and I want to have color be driven by the variable loc underscore mi. And then if we call tmap, run that. Do it down here again so we can see this. Okay. So this is our tmap. We have the extreme high and the extreme low. Okay. But you see most of the values are in the middle. So let's go ahead and plot the p-vals, doing the exact same thing. So I'm going to copy and paste this code. This case, we want the color to be driven by our loc mi underscore p-val. Run that. And then we're going to call tmap underscore p-vals. And then we're going to map that. So in this case, what we want is we want the ones that are very low. But even this isn't particularly helpful, because you can see here that we have a lot of areas that appear to be far greater than 0.05, And 0.05 is in the same category here as the 0.2. So what we actually can do is we can extract only the significant values. So what we can do is we can call a new polygon called GEO called Georgia underscore sig for significant values, and we'll set that equal to GEORGIA. Index, we want all columns, but we only want the rows where the loc underscore mi underscore pval is greater than or equal to, or sorry, less than or equal to 0.05. So if we run that, oops, we actually have to specify, we have to specify the data, GEORGIA at data $. Run that. Okay, there we go. So now that we've got that, now if we call a new tmap, we want tm shape. And what we're going to do here is we're going to call the same thing as before. We're going to call tm shape equals GEORGIA. So we're setting up our base layer, and we're going to call tm underscore bound borders because we don't want the fill. And then we're going to add another layer, so tm underscore shape. And then we're going to pass this shape equals, and this is going to be our GEORGIA underscore sig. Okay. And then now we're going to add tm underscore polygons. And we're going to have the color driven by, again, this time I want the local mi, because we've already assumed that everything in here has a significant p-value. So if we run that, and then we call tmap, and then we examine the plot. So these right here are the only clusters that have significant p-values. And you can see here that we have significant Morans I's that are all strongly positive. So hopefully this makes sense. This sort of step-by-step calculate the neighborhood connectivity, turn that into a weights matrix, calculate your local Morans I, again, making sure to adjust for Bonferroni. And then everything else was just visualizing the results. So hopefully that all makes sense. And if you have any questions, please reach out. Thank you.